Hi everyone, my name is Crystal and I've been working with creative coding for about 12 years now. During this time, I've had the opportunity to do a little bit of everything from web and mobile application development to 3D modeling and VR. I'm also part of the Insights team at Shopify where we create awesome data visualization experiences together. Today, I'll walk you through some of the techniques that I learned along the way so you can create your own interactive and performant experiences with React. If you have any doubts, questions, or suggestions, I'll be available to answer them by the end of the talk, or feel free to reach out to me directly on Twitter. My username is Crystal Campioni. Before we actually start talking about code, there's one topic that I always like to cover because I think it's super important. Motion is a message. If you think about it, in real life, things don't, just pop in your face. It would be really, really scary if they did. Instead, what happens in real life is that things move from one place to the other, like this furry monster walking in real life from one side of the screen to the other. The thing about motion, though, is that when used wrong, it can actually make the experience worse. So, like almost everyone, I've been obsessing over COVID-19 data since the beginning of the pandemic. And as I live in Canada, I always come across this one from a Canadian newspaper. So, have a look at this example. When we switch from total to breakdown, all of the areas representing the breakdown slide down, and the area representing the total slide up. Because everything is moving at the same time, it seems like both of the data sets are not related at all. Um, this is not good because then the relationship between the number of deaths recovered and active and the total is not super clear. So let's compare this with an alternative. So here, instead of everything sliding up and down, we keep the area representing the total always there, and we only slide up and down deaths recovered and active. The relationship does feel a bit clearer, right? But to be honest, this is a perfect example of when using fancy animations is not ideal. So let's have a look at a final alternative. Here, instead of anything sliding at all, we only have a simple fade that reveals and hides the layers of data. This is great because then my eyes don't have to follow some lines moving randomly around. It's just there. So the relationship between both of the data sets is completely obvious. There are, of course, lots of situations where motion can help us understand the message. So let's have a look at another example. Here we have a chart that represents the number of sales from this year with the same period of last year. We can choose which period we'd like to compare, this week, this month, or this quarter. And notice how when we are comparing this quarter to last year's quarter, the line is red because the total number of sales in that quarter was lower than last year's. But when we switch to this week, the line becomes green, as this week, compared to the same week last year, had more sales. The motion here is helping us understand what's going on. So when we choose the period to analyze, we zoom into that period, helping us understand that that specific period belongs in a longer timeline. And the same thing goes about the transition of the color. It helps us understand if the result is positive or negative. So another example. Another example. This chart shows the number of page views in the last 10 minutes. So we have 10 bars, one bar representing each minute. And what's interesting here is that the bar for the minutes now keeps growing as it receives new data. And when a new minute begins, it pushes all of the other bars to the side, making way for itself. So once again, the animation here is helping us reinforce what's going on. Okay, so let's start talking about one example. Recently, we were exploring how to represent the customer behavior data of people accessing Shopify stores. So this was our initial draft. The idea is that we would have all of these moving particle buckets for people that already purchased something, that are checking out, or that just have active cards in the last 10 minutes. It would be super cool if we could see all of those particles swimming in there. And then when a person moved from, let's say, active cards to checking out, we would see that little microbe jumping from one petri dish to the next one. The problem was that we could not actually track what each individual was doing. So the data that we got for this component looked something like this. As you can see, we only have one number for each one of the buckets. There's no way of knowing which one of the little microbes jumped from one petri dish to the next one. So we thought that maybe we could implement the animation of the little microbe jumping from a random direction into the petri dish. But this could get really, really messy if we had like hundreds or thousands of people accessing the shop at the same time. I mean, this this looks kind of cool. All of those three evil blobs floating around in there, but it doesn't actually tell me anything about how many people are at each step of the funnel or how the flow is going. So this was not going to work. This was our second try. So I think that this one is much better because we have three circles with different sizes that are super easy to compare. So we can quickly know if we have more people with active carts or people that already purchased something in the last 10 minutes. We could also make it work with the data structure that we had. So let's say that the first time we receive data, total checkouts is 15. The next time we receive it, total checkouts is 17. So we know for sure that 2 people checked out in that period. So we can trigger an animation of 2 running dots going from active carts to checking out. And we could do the same thing if the number of purchases increased. So let's see how we could start implementing that with SVG and D3. We talked about, I mean, we have all seen how D3 is a powerful tool, and we've seen like awesome examples of what can be created with it, but it can be really overwhelming to know where to start. So this is a screenshot from D3's API reference from their GitHub docs, and look at the size of this thing. D3 is a really complete tool. It has all sorts of methods that you can use to treat the data, bind it to the DOM, etc., etc., etc. But since we're using React to take care of the DOM for us, let's define what we should not use from D3. So that would be things like D3 selections. So this module works in a similar way to what you would expect from something like jQuery, by selecting DOM nodes directly and transforming them based on the dataset. We do not want to use this module because we'll be letting React do what it does best, take care of the virtual DOM in a performant way, and we'll use D3 for what it does best, which is for being a toolbox of math utilities and layout calculation functions. So no D3 selections. A perfect example of the kind of things that we are going to use from D3 is D3 scales. Scales are functions that map from an inputs domain to an output range. So this means that we could, for example, get an input array of values and map it to the available screen space that we have. So in this example, we have an input array that goes from 0 to 150 and 500. And then we can use D3 extent method, which basically gives us back the minimum and maximum value in the array that we have. And then we create finally the scale. D3 scales are actually going to return a new function that you can call every time that you want to pass in a value and retrieve the mapped value from that scale. So in this specific case, we are using the scale to calculate the CX position of each circle that we have on the screen. So basically the horizontal position of each one of those circles. So it would go something like this. The first time we would pass in 0 because that's the value, and we would retrieve back 0 pixels. The next time we would pass in 250 as a value and retrieve 170 pixels. And the last time, 500 as a value and retrieve back 330 pixels. So going back to the customer's behavior chart, now that we know how scales work, we can start exploring how we can change the size of each circle using a D3 scale. The first example that we saw was a linear scale, but using linear scales for calculating the radius of a circle is not ideal because we humans, we tend to interpret the area of things to be the representation of the value. So instead of using a simple linear scale, we can use a scale square root so that the area of the circle represents the value and not simply the radius. We can then use the radius scale to calculate the radius of each circle depending on the data. This is nice, but we are not animating the radius yet, so let's fix that by plugging in React Spring. To do that, we first import use Spring animated and config from the package. Then we set up the animation with the use springs hook. It works something like this. The first argument is the number of springs or animations to create. The second argument is a list of objects describing each of the animations. It is here where we tell React Spring what properties it should watch for changes in order to animate. In this specific case, it's the radius property, where we are using the radius scale to get the value based on the data point. The config is where we define the characteristics of the animation using Spring physics, so things like mass, tension, and friction. Config.molasses is just one of the defaults from the package. If you'd like to learn more about how Spring Physics work, I highly recommend Josh Kummel's article, a friendly introduction to Spring Physics, that you can find on this link, bit.ly/Spring Physics. It's really nice, this article, and it also has like lots of examples that you can play around with these cute dumbbells to understand what each individual property is doing. Once we have the radius spring prepared, we just have to render it. So for that, we replace the regular circle with a animated.circle tag. And instead of calculating the radius directly, we get the radius from the radius spring. And finally, we can implement the running dots animation when we fetch new data. Similarly to what we did for the radius, we'll be using the use springs hook to implement the animation. To define the number of dots that should be rendered on the screen, we have to keep track of the data changes. And for that, we use a custom use previous hook. And once we have a way of keeping track of the previous value, we can observe for changes in our data using a use effect hook that has data as a dependency. Oops, sorry. Okay, so inside that hook, we first check if the count has increased before doing anything else. We then calculate the increment size by comparing the current value with the previous count. The increment will be used to define how many running dots we should render on the screen. The animation happens quite fast though, so we can't really tell the difference once the number of running dots gets too high. I mean, it's easy to count when you have like 5 running dots, but if the increment is big, like let's say 100 or 200, you can't actually count them. So we can take advantage of that for a quick performance gain. Since we can't tell the difference if there are like 50, 100, or 2,000 running dots, let's just clamp it so it never is more than maximum circles per bucket. Then we create an array of objects that we'll be using in the springs animation. So basically describing each animation inside of the use springs animation. So by using the array method, we pass in the increment size so we can create a new array of that length, and we fill it with objects describing the animation. There's a lot happening in there, so let's have a closer look. If you create an array by using the array method and passing it a number, it will create an array of that specific length. You can then use the fill method to fill it with anything that you want. So it can be either a nose, it can be strings, or in this specific case, it can be an array of objects. And each object is going to have a x from x cx position and a to cx position, describing where the animation should start and where the animation should end. And it also should have the radius of that specific running dot. So the radius in this specific case, remember that we talked about not being able to notice when it was a big increment or when it was a small increment. So instead of just keep increasing the count of running dots, what we're going to do instead is use a small dot to represent a small increment and use a big dot to represent a big increment. So that's exactly what the get running dot radius method is doing here. If it is a big increment, display a big dot. If it is a small increment, display a small dot. And finally, we can use the array of objects that we just created to actually implement the animation with the use springs hook. It's really similar to what we did before, but there are a couple of differences. The first thing to notice is that we are applying a delay to each of the dots based on its index. If we didn't do that, all of the dots would run at exactly the same time and would be on top of each other, meaning that we would only ever see one dot every time that the data changes. By applying a delay, we create this trail effect as if one dot was following the previous one. Then, instead of just animating a value every time that it changes, we are defining where the animation should start and end with a from and to object. Each of the properties inside of these objects will be animated. Here's how it looks in the end. We have small running dots for small increments and big dots for big increments. And the radius of each bucket keeps changing depending on how many people are in each step of the funnel. All right, so now that we saw how to implement that chart using SVGs, let's talk a little bit about performance. So SVGs use what we call a retain mode API, meaning that we can always refer back to what is being rendered on the screen because we have access to all of those tags that live inside of the SVG. This makes it super straightforward to implement animations with SVGs because we just have to update the values of the attributes in each tag. If you have to implement a huge amount of animated things though, you will start to notice that the more animated elements you have on the DOM, more the performance will drop. So that's when you should use Canvas. The main difference is that Canvas use what we call a immediate mode API. This means that there's no way of keeping track of what objects we currently have on the screen like we did with SVGs, and instead it works as if you had a literal blank canvas and a paintbrush. So you can give commands to this paintbrush so it draws on the canvas, but once it's there, it's there. There's no way that you can actually move the paint around. So you might be thinking, how on earth are we going to animate things then? And to answer that, I'll ask you to think of one of those paper flip books. I used to love creating those when I was a child. And it's the same process for animating with Canvas. Since you can't actually move the paint around, you just have to redraw everything at its new position at every frame. So going back to the customer behavior component, if we were to re-implement it with Canvas, we wouldn't use animated.circle anymore. Instead, we would redraw the whole canvas. With each circle in its new position and with its new size at the same time. So let's have a look at a simple example. Suppose we wanted to have a circle moving right and left on the screen, and we would also want to render its position as text. We could once again have the use spring hook that updates the X position. And then we could have an animated.ziv element to render the position as text on the screen. The animated that we import from the library can also be used to create custom animated components though. So in this specific case, we could have a canvas component that receives X value as a prop and then redraws the canvas every time that X changes. So in the first lines here, we have a ref that we can use to access the canvas element. And then we store the context 2D of that canvas in a constant so that it's easy for us to access it. The context 2D is basically what has all of the methods that we'll be using to draw on the canvas. And after that, we have a use effect hook that keeps track of the changes in the X value. And inside of that use effect, a draw method that clears the whole canvas every time that the value changes, the first thing that it does, and then calls begin path to our begin path. But when you begin a path in Canvas, that path is invisible. So after that, we have to actually fill it. So we begin a path, we draw a circle, and then we fill it with red. Finally, we export the canvas as an animated canvas by using the animated method that we imported from React Spring. Once we have the animated canvas, we just need to import it to the parent component that has the useSpring method, the useSpring hook being called, and pass down the X value the same way that we did with animated.ziv. So we could do the same thing in the customer behavior component by passing the radius spring and the order running dots to the animated customer behavior canvas component. The Canvas API is quite verbose though, so let's make our lives easier by introducing a couple of utility functions that we use quite often. A draw circle that takes in the context, x and y coordinates for the origin, a radius, and a fill color. A draw rect method that takes similar arguments to draw rectangles on the screen, and a clear canvas method that uses the clear rect method to clear the whole canvas. With these utilities in place, we can go ahead and include a use effect hook that gets called every time that bucket radius or the running dots array changes. The order that these methods get called also matter. We first want to clear the whole canvas, then we draw each animated element in its new position, and finally we draw the static elements on top of everything, because in this specific case, the static elements do appear on top of the animated elements. What the draw animated element method does is map through each radius value in the bucket radius array that we got as a prop from the use spring hook, and then use the index to determine the x position of each circle, and the y position for each circle is the same. We then fill it with the gradient, remembering that the two first buckets are gray and the last one is green. And we finally draw them with the new radius depending on the value that we currently have in that specific bucket. Lastly, we do the same thing for the running dots. Get each dot cx, fill in radius position, and use the draw circle method to draw them on the screen. Lastly, I would like to go through a quick note on accessibility. Even though animations are super cool and they can definitely help us tell a story, it can also be a horrible experience for people that are sensitive to motion and can get dizzy by things moving around on the screen. Many operational systems have use reduce motion options to basically disable animations for people that have this sensitivity. And we as developers should check if the user prefers reduced motion or not. In our projects, we have a use reduced motion method hook that takes advantage of window match media to check if the user prefers reduced motion or not, and returns true or false accordingly. This plays really nicely with React Spring, as it accepts an immediate mode prop that basically disables the animation if we set it to true. And also, we should make sure that what we are rendering on the screen as an image has a semantic representation so that folks that are using screen readers can also understand what's going on. Canvas, everything that you put inside of the canvas is considered subdom. So that's basically the fallback for all browsers that do not have access to Canvas, like, for example, screen readers. And since Canvas is just an image, you have to think about what the semantic structure for that would be if you were to represent it with text. Our customer behavior component could easily be replaced by a table, right? So we have a table that has active cards, checking out, and purchased, and a number representing how many people we have in each one of those steps. So we basically have to place a table that also gets the values updated every time inside of that canvas. And the same thing goes for SVGs. Since we already have the elements that represent each part of the table being rendered in the SVG, we do not have to add any extra elements. We just have to make sure that we give the appropriate roles to the SVG tags so that it gets read as a table by screen readers. So in this specific case, we can give the SVG element a role of table, and then give the table header for the labels and the rows with cells as well. And yeah, I guess that's all that I had for today. Thank you so much for following along. I hope you found this presentation useful. As I mentioned in the beginning, if you have any doubts, questions, or suggestions, either talk to me now in the end of the talk, or just reach out to me directly on Twitter. And we are hiring. Shopify will hire 2021 developers in 2021. So if you're interested in coming work with us, just reach out to me directly or visit Shopify's career website.